All right. Welcome to my channel. This channel is for educational purposes, and we look at great theories of everything and try to do a deep dive on them, show you them in detail, and give you suggestions about how you might incorporate these things in your life. Today is our 474th video that we've done on the reciprocal system of theory from Dewey B. Larson. And in 1959, Mr. Larson proposed his two fundamental postulates about how the universe operated. The first postulate basically stated the case of how the universe originally his original ideas about how the universe operated, and then the second postulate basically gave him the instructions for constructing a theoretical universe from that first postulate. And then he did go through this process of deduction and derived a theoretical universe, and then compared his theoretical universe with the measured empirical universe of the legacy scientists, and published those results in a number of different works, including the one that we're looking at today called Basic Properties of Matter. This is a book he wrote in 1987, just 3 years before he died. And this book, we are in chapter 8, which is called Temperature Relations. And in this book, Larson arrives at a number of different equations for the basic properties of matter, like the melting point, or the compressibility, or the specific heat, or the thermal expansion. And then puts all of the atoms and many compounds into his equations and pumps them out with values, and then compares his values with the values that have been determined by the legacy scientists in their laboratory experiments and published in their scientific tables. Okay, now Larson's first postulate states that the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. Okay, so those are basically 4 prongs of that first postulate. Universe is made out of motion. Motion is the relationship between space and time. Space, time, and motion come in 3 dimensions. Space, time, and motion come only in discrete units. Now, Larson is not the first person to propose a universe constructed out of motion. Other luminaries such as Thomas Hobbes, or René Descartes, and Arthur Eddington have all attempted to construct universes upon motion, as opposed to matter or energy or force. But they were unable to make a system work, really probably because they didn't redefine what motion is. Now for Larson, when he refers to motion, he's referring more generally to motion, a more generalized kind of motion that he calls scalar motion. A scalar motion is a motion that has been acknowledged by science, but not recognized in its importance. And a scalar motion is a motion that has a magnitude, but it has no specific direction. And so you can envision a scalar motion using a balloon that you put dots on. Or if you wanted, you could use something like raisin bread. And as you blow up the balloon, all of the dots will be moving away from each other. As you heat the bread, all the raisins will be moving away from each other. But they won't be moving in any specific direction. Every point on that balloon will be moving away from every point. Basically, every point will be moving in every direction, or at least every outward direction. And so you can't impute any type of vectorial direction to any of the dots on the surface of that balloon. Larson calls that outward motion the progression. And then if you reverse this motion, all the dots will be moving toward each other. But again, they won't be moving in any specific direction. They'll be moving in all directions. Every dot will be moving toward every other dot. And this is what Larson refers to as gravitation. And really, matter, the formation of matter, is really the conversion from the progression, which is, in Larson's system, this is the source of this universe. The progression is occurring at all times, in all places, eternally. So this is the source, the neutral point or the null point of this universe. This is the state of rest of a universe of motion. That is a conceptual hurdle that you have to get over to be able to understand the reciprocal system, is that you have to be able to conceive of motion without anything moving. Motion itself precedes anything that would be moving. And motion, in fact, composes anything that would be moving. So any matter or anything else that you get from motion is also motion. And so the manifestation of matter and aggregates of matter is the result of reversing that outward motion of the progression and turning it into an inward motion of gravitation. And that is done with a number of different reversals and then rotations. Larson has a periodic table where he signifies his elements with three numbers, two-dimensional rotations, and the A and B, and C is a one-dimensional rotation that is optional, which is 0 in the noble gases. And so that gives you an idea. Then Larson takes those numbers and he uses them to determine the equations that he arrives at in this book for the basic properties of matter. They come from those original numbers that are identifying the atoms of the periodic table. Now, Larson defines motion as the relationship between space and time. It may seem nonsensical. What it means is that space and time do not exist in and of themselves. They only exist together in motion, and that space and time are reciprocals of one another. As you go out in space, you go in time, and vice versa. They're just like mathematical reciprocals. The reciprocal of 3 is 1/3, 3 over 1 and 1 over 3. They both have the same ingredients, but they have them in reverse order. And you move out in one, then you move in the other. And an example of, so basically for Larson, motion is a fraction with space or time as the numerator and time or space as the denominator. So for example, speed, the bicycle is moving 15 miles per hour. 15 miles of space in 1 hour of time. Space over time is speed. But he extrapolates that to all of our scientific phenomena are forms of motion, and they are all fractions with space or time as the numerator and time or space as the denominator, such as matter. In Larson's system, matter is space to the third power. It is time to the third power over space to the third power. And all of our other kind of scientific units have their own time-space signatures or space-time signatures. Now, if you decided that you wanted to double the speed, you could say now the bike is moving 30 miles per hour. But equivalently, you could also say the bike is now moving 15 miles per half hour. You can double the speed, double the space, or you can halve the time. Both of them will serve to double the speed. So you can see that reciprocal relationship there. And that, again, extends to all forms of motion, not just speed. And in Larson's system, space, time, and motion come in 3 dimensions. Now you can see this if you abstract that that balloon motion, say the inward balloon motion of gravitation, and scalar inward motion, and you arbitrarily decide to appoint a reference point, to assign a reference point to one of the dots. You say, this particular dot, I proclaim that it is motionless. This dot is not moving. All the other dots are moving in respect to this other dot. What you will see is that all of the dots are moving toward that one dot. And it will look as if they are drawn toward it by a gravitational field, that there is some kind of pull that's moving one of the dots, moving all of the dots toward that one, that there's a gravitational field emanating from that first dot, but the reference dot. But that's not the case. Every dot is pursuing its own course. They are all moving toward each other. But then when you suspend the motion of one of the dots, then that its motion toward all the other dots is basically transferred to all the other dots. Now, if you do that, you will find that you have what Larson calls a spatial, stationary reference system. So you will have, and you can view this in our universe. This is what Larson calls the container viewpoint. As we move, and this is somewhat of an obstacle of understanding Larson's system, but it's still part of his system. In that we see our world as stationary in space, 3 dimensions of space, XYZ coordinates, and time is unfolding. Events are unfolding in time. Time is getting later and later and later. So this is what Larson calls the stationary spatial reference system. 3 dimensions of space in a still frame, coordinate space, and what Larson calls clock time. The clock is always getting later and later and later, but in no specific direction, in a scalar manner. And so what's happened is that the gravitation has provided this level of stillness so that we are able to see space in its 3-dimensional stationary aspect, while time continues to progress the same way that it would on the surface of an expanding balloon. Now, by the reciprocal postulate, knowing that space and time are identical except that they are reciprocals of one another, there would also theoretically be a place where you would have 3 dimensions of time in a still frame. Time has been stopped, and space continues in a scalar manner. So space would still be moving farther and farther and farther apart, like on the surface of an expanding balloon in no particular direction, outward or inward. And Larson refers to that as the temporal stationary reference system. Coordinate time and clock space. Now, both of these reference systems, you got your 3 dimensions of time and you got your 3 dimensions of space, but recognize that it only requires 1 dimension of motion to occupy all 3 of those dimensions of either time or space. So if you have 3 dimensions of motion, that means that you are exceeding the capabilities of either one of those reference systems. Those reference systems are not sufficient to describe Larson's universe of motion, because he's using 3 dimensions of motion, not just 3 dimensions of space or time. I guess accommodating that, Larson is using what he calls the natural reference system. And the natural reference system is when you take that progression and you assign it a speed. And the speed that you assign it will be coming from that discrete unit postulate. Space, time, and motion come only in discrete units. You have to have a full unit of space before you have space. You have to have a full unit of time before you have time. And if you have 1 unit of space per 1 unit of time, space over time being speed, then you have what Larson calls unit speed. 1 over 1 equals 1. And unit speed also works out to be the speed of light. And that is the progression of the natural reference system. The progression at 1 unit of space per 1 unit of time at all times in all places, eternally. And so Larson refers to that as the progression of the natural reference system. This is a moving reference system. Now you have to also regard that this is in 3 dimensions. That is the source, and what Larson calls the null point or the neutral point, meaning that half the universe is actually moving faster than the speed of light, and half is moving slower than the speed of light. Half that's moving faster, Larson calls the cosmic sector, and that is where you've got your coordinate time in your clock space. The half that's moving slower is the half that's familiar to us and to legacy science, and that is called the material sector, and that is where you have clock space, clock time, and coordinate space. Now within both the material sector and the cosmic sector, you have a mini region within either one of them. In the material sector, this has to do with the discrete unit of space. When 2 atoms or particles or molecules approach each other to 1 unit of space, which is approximately 2 millionths of an inch, then they cannot move any closer because you can't get any less than 1 unit. And so instead, they move outward in time, which is equivalent to moving inward in space, and which we see as moving inward in space because we are anchored to the spatial reference system. And so we only see space, we don't see time. And so Larson refers to this as the time region. The time region is the region inside 1 unit of space. And he refers to our view of that as equivalent space, We don't see time, but we see time's equivalent of space. Now, what we see is distorted. Equivalent space we see as a second power region, and equivalent is like a projection on the wall. And we also, what we see needs to be reduced by the interregional ratio. We don't see the whole picture. We see only a small fraction of what's actually going on. The same thing holds true in the cosmic sector, only this is where two cosmic atoms or two cosmic molecules approach each other to 1 unit of time, which happens to be about 1.5 times 10 to the minus 16 seconds. And when they get that close, then they cannot move any closer in time, and so instead they move outward in space. That they, a dweller in the cosmic sector would see that in equivalent time. All right, sorry about that interruption there. My phone just overheated and had to let it chill out for a little while. I had basically gotten done talking about the ins and outs of the reciprocal system, and we're going to start reading from chapter 8 here on thermal expansion in the book Basic Properties of Matter. He just was talking about extending the temperature into a second unit, which is the three-dimensional unit. And to be frank, this stuff is really difficult for me, and I'm having trouble grasping it. I'm just going to read it into the record and let it marinate in my head a little bit more. Maybe I'll figure it out. Maybe you'll figure it out, and you'll show me how to do it. But let's start right here. As brought out in chapter 7, the minimum of the 0-point temperature, T sub 0, is equivalent to one of the 128 dimensional units that correspond to one full temperature unit, 510.8 degrees Kelvin. As the temperature rises, additional units of motion are activated, and the corresponding value when all 128 units are fully effective is thus 7/2 times 510.8 equals 1788 degrees Kelvin. Okay, now I'm under the impression that this is the liquid temperature and that the 7/2 comes from seeing that the T sub 0 is 2/9, but the T sub 0 extends into a negative level when you're talking about in the time region, but outside of the time region, then you don't, it extends just into the solid state, and so you don't need 9/2, but you only need 7/2 to get to T sub 1. Okay, under the same maximum conditions, the second unit of thermal motion from T sub 1 to the solid endpoint. Okay, we're still talking about a solid here. I guess we're just talking about multi-dimensional motion outside, past T sub 1. The second unit of, or maybe just past T sub 0. This is T sub 1. The second unit of thermal motion from T sub 1 to the solid endpoint adds an equal magnitude. Thus, the temperature of this theoretical full-scale solid endpoint is 3,576 degrees Kelvin. The total expansion coefficient at T sub 1 on the first segment of the expansion curve and at the initial point of the second segment is then, so this is the coefficient, so this is the kind of the rate here, is 0.0205 over 3576. And that 0.0205 was the index of expansion that he figured out, earlier in this chapter. However, this coefficient is subject to a 1/9 initial level. This makes the net effective coefficient 8/9 times 0.0205 over 3576 equals 5.2 times 10 to the minus 6 per degree Kelvin. Okay, so that's just like 1 over temperature, or scalar over temperature. Okay, where the endpoint temperature, which we are equating to the melting point, tin, or T sub m, the melting point for present purposes, is below 3576. The average coefficient of expansion is increased by the ratio of 3576 over T sub m. Inasmuch as the total expansion up to the solid endpoint is a fixed magnitude, if the first temperature unit up to T sub 1 were to take its full share of the expansion, the coefficient at T sub 1 on the first segment of the expansion curve and at the initial point of the second segment would also be increased by the same ratio. But in the first unit range of temperature, the thermal motion takes place in one time region, dimension only. And there is no opportunity to increase the total expansion by extension into additional dimensions in the manner that is possible when a second unit of motion is involved. Additional dimensions do not increase the effective magnitude of one unit, as 1 to the n equals 1. I believe this is what that says. The total expansion corresponding to the first unit of motion, or speed, can be increased by extension to additional rotational speed displacements, but this is possible only in full units and is limited to a total of 4, the maximum magnetic displacement. As an example, let us consider the element zirconium, which has a melting point of 2125 degrees Kelvin. The melting point ratio is therefore 3576 over 2125 equals 1.68. Inasmuch as this is less than 2 full units, the expansion coefficient of zirconium remains at 1 unit, 5.2 times 10 to the minus 6 per degree Kelvin, at the initial point of the second segment of the curve, and the difference has to be made up by an increase in the rate of expansion between this initial point and T sub m. That is, by an increase in the slope of the second section of the expansion curve. The expansion pattern of zirconium is shown in a graph here on this page, which I don't have. Now, let us look at an element with a lower melting point. Titanium has a melting point of 1941. The ratio of 3576 to 1941 is 1.84. This again is less than 2 full units. Titanium therefore has the same 1 unit expansion coefficient at the initial level as the elements with higher melting points. The melting point of potassium is only a little more than 100 degrees lower, or I'm sorry, not potassium, but palladium, is only a little more than 100 degrees below that of titanium, but this difference is just enough to put this element into the 2 unit range. The ratio computed from the observed melting point is 1825 Kelvin, and that is only 1.96, and is thus slightly under the 2 unit level, But in this case, the difference between the melting point and the end point of the solid state, which we are disregarding for general application, becomes important, as it is enough to raise the 1.96 ratio above 2. The expansion coefficient of palladium at the initial point of the second segment of the curve is therefore 2 units, meaning 10.3 times 10 to the minus 6. And the expansion curve follows the pattern illustrated in the second curve on figure 14. Larson's explanations make it almost more difficult than it was in the first place. Why doesn't he use an element that is actually above 2.00, just to give you the basic points, as opposed to choosing one that complicates the whole matter even more. So anyway, I'm a little frustrated with this right now because I'm lost for the 100th time going over this material. I'm still trying to figure out these temperature relations in the thermal expansion. Every time I think I have it, he throws in a curveball that confuses me. So I'm working on it. In the meantime, thanks for tuning in. And, keep working on it yourself. Don't get discouraged because, you go over this and eventually something clicks. Okay. Thanks for tuning in and have a great day.